This is Glyph. That is a very large number on the presenter display that I can see here, so I'm not going to interrupt him anymore.
Hi, everybody. I'm Glyph. Welcome to my talk. A lot of other speakers have told you about their kids, their cats, their interests, but I'm just going to tell you about my website, which is glyph.im, for 3 reasons. First, I want to keep this introduction quick. As Gritch mentioned, the number is very large. Second, because it's better OPSEC. And third, so I can tell you to go there to sign up for my Patreon or GitHub sponsors or whatever to support my independent work so that I can legitimately declare my expenses for this conference as tax deductible as a promotional expense. So, hi everybody. It's great to see you here at ExcavateCon, the premier Northern California conference for mechanical excavators and industrial mechanical excavator accessories.
Python conference.
What?
It's a Python conference.
Python? Like the programming language? Why are we in a barn? There's like a bunch of equipment outside for like mechanical excavation. Whatever. Okay, it looks like I brought the wrong slides, but sure, Python. I do know a lot about Python, so I can like riff about that later on, I guess. I mean, you all know a bit about earth-moving equipment, I'm sure, and it has a lot in common with Python, so we'll make it work. Anyway, welcome to my talk, Back to Backhoes, the history and evolution of industrial and commercial mechanical excavation technology. Anyway, with that out of the way, let's get started. Up front, I want to be clear that a lot of this initial section is cribbed from a book. When I was invited to ExcavateCon, I was not much of an expert on mechanical excavators, so I needed to read up. The Innovator's Dilemma, When New Technologies Cause Great Firms to Fail, by Clayton M. Christensen. This is a great book. I do recommend that you read it. In comparison to a lot of business books, which are full of like vibes and inspirational quotes, this is jam-packed with data. You might say that this book gives us a strong bedrock of facts and data upon which to build our understanding. I'm sorry. In 1837, the first mechanical excavators were steam-powered and cable-actuated. As I'm sure any ExcavateCon or North Bay Python, I guess, audience knows, these large machines revolutionized several significant earth-moving applications, including canal construction, such as the Panama Canal, railway construction, and strip mining. Steam-powered, cable-actuated excavators made industry possible. There were simply not enough human hands to move enough earth. I really want to stress this point, because when we talk about legacy technologies, we often deride them as like bad and old. The existence of new and improved implies the alternative is old and busted. But that's not really how technology works. These minerals that steam power and cable actuation pulled out of the ground are crucial to the foundations of our current technology and industrial landscape. While some technologies, like steam power, are indeed obsolete because comprehensively better alternatives exist, that doesn't mean that the entire generation of technology is obsolete. But before we get to the innovation that obsoleted steam, let's talk about how the purchasers of steam shovels thought about evaluating those excavators. In the applications that I mentioned, canal construction, railway construction, and strip mining, the focus of the buyer was always on the bucket. How much earth could the bucket move? How far could the bucket extend? Bigger buckets, more earth, faster moving, further reach, better excavator. All these use cases involved really, really big buckets of earth. The first interesting technology to look at in the historical development of mechanical excavation is the advent of gasoline power. Gas power was a revolutionary technology which increased the power, speed, and general efficiency of the bucket. You could move more earth. However, the fact that it made a large change to the excavator industry does not mean that it made a disruptive change to the industry. The biggest distinction that the Innovator's Dilemma draws, and if you've ever heard people talking about this on like Hacker News or whatever, is this distinction between a sustaining technology development and a disruptive technology development. Gasoline power improved the power and efficiency of excavators, but it sustained the existing companies selling excavators because they could just take a gas engine and hook it up to their cable actuation. So let's talk about the introduction of a disruptive technology, hydraulic actuation. Just a brief review, because I guess this isn't actually an excavator conference, maybe it'd be good to mention this. A power technology is the technology that generates the power and focuses it enough to be put into some application. And an actuation technology is the one that moves the power from where it is generated, the boiler or the engine, to the place where it is needed, like the joint that moves or lifts the bucket. So here we can see a cable-actuated bucket. You can just look at those beautiful cables. As you can see, they pull on the arm, they pull on the bucket. Gas and steam engines put out energy that's like turning a crank really fast. The crank's attached to a winch, which looks like this, and it kind of makes a sound like this. And then hydraulic actuation is accomplished by applying pressure to a fluid in a sealed chamber, which exerts pressure to extend or vacuum to retract a rod. Now, when they were first introduced, that fluid chamber had to be sealed, and the hydraulic seals were so much weaker than steel cables, it limited the strength of the excavator. In particular, the first hydraulics were simply too weak to be suitable for any of the existing use cases of cable-actuated excavators. Railways, canals, strip mines needed to move huge amounts of earth, and they purchased their excavators for that purpose and didn't care about this new development of hydraulics. However, hydraulic actuation technology is much more compact than cable actuation technology due to the need for large spools of cable and like all the room you need to keep these giant cables under tension to lift the shovels up. Therefore, it was possible to use in entirely new environments where large, bulky, cable-actuated tech was impractical. Hydraulics were, in fact, so small that they could be put into places that could not ever accommodate a cable-actuated steam shovel, such as the back of a small farm vehicle, such as a tractor, like the one outside. I'm still not totally sure this is like a Python conference, but whatever. Okay. Now I'm just going to quote directly from the book. Small residential contractors purchased these units to dig narrow ditches from water and sewer lines in the street to the foundations of houses under construction. These very small jobs had never warranted the expense or time required to bring in big, imprecise, cable-actuated, track-driven shovels, so the trenches had always been dug by hand. Hydraulic backhoes attached to the back of highly mobile tractors could do these jobs in less than an hour per house, and they became extremely popular with contractors building large tract subdivisions. So I must emphasize, the people buying backhoes attached to hydraulically actuated diggers were customers who had never even considered buying a cable-actuated excavator. Hydraulics were not competing with steel cable-actuated excavators. They were competing with human hands holding shovels, doing everything manually. So there were many reasons that backhoes and, by extension, hydraulic actuation were just not a serious technology that the mechanical excavation industry would ever care about. Given the inherent superiority of the much more powerful and larger cable-actuated excavators, there was only one place that the excavation industry could go next, which was, of course, the total destruction of all of the cable-actuated vendors. You see, during the tract house building boom, there was tremendous demand for hydraulic excavators from home builders, which meant that the new hydraulic excavator companies that had entered the market had a ton of profits to reinvest in their businesses, to reinvest in the development of hydraulics. In this graph from the innovator's dilemma, we can see that as hydraulic excavators were rapidly increasing in bucket capacity, the increase in demand for larger bucket sizes from contractors across the more intense industrial parts of the industry was quite slow. Once hydraulic actuated buckets crossed that threshold of the largest that the industry demanded, the hydraulic manufacturers took over. So today, many of the largest excavators used in strip mines and subway construction and canal construction all use hydraulic actuation, and the companies that develop the hydraulic actuation technology are by far the most successful. Which does raise the question, if hydraulics were the future, why didn't the companies making cable-actuated excavators simply switch over to hydraulics? The thing about hydraulics is that they were smaller and less powerful and less expensive, and thus lower margin. That meant that at any point along the life cycle of the cable-actuated excavator company, it made sense to go upmarket. You make your buckets bigger, you make yourself more attractive to the more well-capitalized customers with the more sophisticated needs who need to move more earth. You make the cables more powerful, the buckets even bigger. You take the CEO of the world's biggest strip mine out to dinner, you really lay it on thick, everything depends on this deal. You start out selling a few hundred tiny excavators, you're selling a couple dozen really big ones, and pretty soon you're selling the biggest possible cable digger to the biggest possible project, but then after that, you're selling 0 cable diggers to 0 customers because everyone's just using hydraulics now. They're much smaller, they're much cheaper. The innovator's dilemma describes this phenomenon in depth, but it doesn't give it a catchy name. Personally, I refer to it as the upmarket death spiral. The problem with this phenomenon is that it is not caused by bad management. Bad management wastes resources, pursues unprofitable strategies, doesn't pay attention to market research data, doesn't listen to customers, but in the short term, it is always entirely rational to want to pursue bigger, higher margin, richer customers, and avoiding this requires long-term strategic thinking and tactics which are, in the short term, bad. The upmarket death spiral is what the frequently posted business wisdom, variously attributed to executives at HP, Steve Jobs, Sun Tzu, or whoever, if you don't put yourself out of business, someone else will, is really all about. It's very, very hard to try to literally put yourself out of business, though. The innovator's dilemma frequently comes back to the fact that if you want to put yourself out of business, first you need to become someone else. Specifically, if you are a big business, and you've identified a disruptive technology that represents a big future opportunity, the only way to chart a path between the tiny customer base that might initially exist and the future big opportunity is to create what would be called in business lingo a going concern, which means an actually operating business that brings in enough money to support itself, not your gigantic cable-actuated excavator business, but a small track housing hydraulic business. Lots of companies set up labs. Lots of cable excavator companies actually did notice that hydraulics were the future. They tried to manufacture them. They tried to make really big hydraulics way too early in the technology's life cycle. That was a mistake. Their big customers didn't care about hydraulics yet. The smaller organizations that cared about the smaller sales won. What made the hydraulic backhoe manufacturers take over was they were able to create organizations that were independent and themselves of a size that really cared about the few backhoes they were selling to home builders and didn't need to care about trying to sell $1 million shovel to $1 billion strip mine. And, oh, I don't know how this slide got in here. This is a nice opportunity to shout out one of my favorite musical comedy creators, Brian David Gilbert, who has a great talk about caterpillars, which is titled, "This Song is Not a Metaphor." But that's probably not related to the rest of the talk. Wait, maybe these slides are messed up. Let me check something. Oh, there's the Python talk. Okay, cool, yeah. It's like about small pythons or something? Maybe I could say something about Python now. Hi, I'm Glyph. Welcome to my North Bay Python talk, Python in the Small, or how history teaches us that Python will inevitably be destroyed by a smaller, worse language, why that's bad, and what we can do about it. Now, not that the other talk that I started with was a metaphor, but if it were a metaphor, one question that might arise as we attempt to extend the metaphor is, Python's not a company, right? Like, do we even have customers? Are our customers big companies where Python has moved up market, serving the interests of larger and more problematic concentrations of capital? And to answer this, you could just look at the placard that I'm standing in front of. So we could ask, what is small? Smallness is the absence of overhead. Let's review the different types of overhead that Python has to see how small it is already. CPU overhead. Python requires a larger computer because it's really slow to execute. This is generally an uncontroversial statement, but let's justify it. Just as a rough ballpark, this comparison from the Computer Language Benchmarks game, a website that Debian runs to allow programming languages to compete on their performance by implementing various benchmarks, shows that Python is between 10 and 300 times slower than the baseline, which I believe is C. Note that it is one of the worst performers, slower on average than Perl and Ruby. Next, we could talk about memory overhead. CPython has a few different kinds of memory overhead. Loading a Python module into your process loads up your source code along with all your doc strings into doc attributes. Although Python does have very efficient hash tables, they're not as efficient as a C-style data structure with fixed offsets, and every object in your code, from functions to classes to modules to enums, all has an object attached. They all have hash tables hanging off of them. It ends up adding up after a while. This all gets much worse when you multiply it out over a multiprocessing cluster, which you still realistically need today in order to get any CPU parallelism. A single Python process with a bunch of PyPI libraries loaded into it and a fair amount of cache state can easily take hundreds of megabytes, which then blows up. Disk overhead. By convention, a deployed Python artifact includes both bytecode and a full copy of all the source code and a full copy of the Python interpreter. On my Mac, Python takes up more than 300 megabytes. A lot of that is compiled bytecode, the Python test suite, other pieces of overhead you don't actually need in order to run Python code, but even after PEP 594, the removing dead batteries PEP, we still don't have a supported official way to remove any of this stuff. You can delete it, but you have no way of knowing if you're breaking something without actually checking every single thing you still want to work about Python. And if the way that you check that you didn't break anything is you run the test suite, and the test suite is like most of the overhead, it creates some problems. But the most important one is cognitive overhead. Python requires a lot of thinking in order to start and to manage a project. There's like PyProject.toml and virtualenv and UV and poetry and unit tests and integration tests and GitHub Actions and PyPI releases and trusted publishers. And you know what? I don't have time to get into all that right now, but somebody should do a talk about it. So perhaps more relevantly here, there's a lot of cognitive overhead to understanding Python's capabilities and whether things will even work for you for what you want to do. Some of this overhead is kind of out of our control. So consider this dichotomy. If, while I am logged out, I write or simply Google for how do I write an iOS app with Python? How do I write an iOS app? Google's immediate summary of the first article contains 4 steps. Download Xcode, launch Xcode, get familiar with Xcode, build and run your app with Xcode. Now, obviously, that is a little bit reductive. You'll almost certainly need like a 5th step. But when you ask the question this way, you have a very clear, obvious way to a nice happy path experience where you can expect the tutorial to be relatively simple and hold your hand through getting things to work. If instead I Google for how do I write a Python mobile app, I get a content marketing puff piece, which is summarized with 8 key steps, beginning with choose your framework, always a good indication, set up your development environment, initialize your project, and so on. Every one of these points has an ellipsis next to it, indicating a very complex set of abstract instructions that you will need to follow. To be clear, this type of side-by-side comparison is not particularly methodologically valid. You could construct searches that would give you very silly results, but I included it because in this case, that quick glance does accurately reflect the much more complex and difficult process of a newcomer to Python attempting to figure out how to use all these tools that we have built. We have tools like Kivy and Beware, which actually do a lot of this work for you already, but the complexity of the ecosystem means it's hard to find and it's hard to use. This type of cognitive overhead is really the only reason we should care about things like CPU, memory, disk, etc. CPU doesn't matter if it's fast enough. Memory doesn't matter if it fits in your RAM. It doesn't matter if your Python is 300 megabytes as long as it fits on the disk you're going to use. So the thing we should be looking at if we want to be able to fit Python into smaller places is not the hydraulic actuator. As I said, the cable companies had those. They built lots of hydraulic actuation products that were just not sized to their market. It's important to know that there are technical solutions to the technical problems. There are various insmalliners which you can find if you start running into constraints with Python. But my setup of how big and bloated Python is a little bit of a misdirect because these solutions mostly exist already. We've got tools like PyPy, Numba, NumPy, Cython, MyPyC. These can all improve your CPU performance depending on your application. Many of the CPU tools also address some of Python's memory problems. PyPy has a much more compact format and memory for laying out objects, in addition to having a JIT to make your code faster. Declaring your classes with underslots to avoid the hash table overhead can shrink a lot of applications. Using compact arrays instead of collections of objects can shrink your memory footprint by orders of magnitude. Python itself even contemplates the disk space issue, providing tools like Python-m compile all to produce bytecode, and you can just ship your bytecode. Python-oo to optimize out not just the runtime cost of the doc strings, but also their on-disk representation to leave them out of that bytecode. The thing is, the technology is mostly just a red herring. All of these individual problems are eminently solvable with tools you can kind of just Google if you need them. 20 years ago, I put a full CPython interpreter onto an embedded device that played music on school buses, which had less than 512 megs of RAM and ran a full Linux kernel. And in order to compress it down, all I did was I just made our application be PID1. Simple. So what we need to be looking for is not the hydraulic piston. We already have that. We need to be looking for the alley behind the tract house where people are still digging their plumbing hookup ditches by hand, or worse, in JavaScript. And of course, I'm kidding. There's nothing wrong with JavaScript. But the process of learning JavaScript is another big investment that people have to make on top of learning Python. It is more friction in the process. And I said earlier that the disruptive technology needs a going concern to be properly developed. It needs people using it, finding its flaws, having a tool that is matched to a market. The rubber really needs to be meeting the road. And here's an example of a backhoe in the Python community. PyScript has been out for 3 years. It's amazing. It can, in theory, fit Python into that plumbing ditch just fine. This metaphor is really getting away from me, but let's try to land that plane. It's not like it can't work. Lukasz Laga built this 3D game that runs in a web browser in less than 300 lines of Python in a couple of hours a few years ago. The technology exists. You can use it today if you want. There are so many cool demos. So if it works, I've got a demo of it working, why do I say it doesn't work? Surprise, turns out I only give talks about CI. Because the thing that you need is the continuous integration. If you go to the PyScript website, it's all demoware. There are no testimonials, no look at this web app using PyScript, no here's a logo of one of our customers, just a link to a bunch of documentation examples and a Discord. Because the hallmark of a real going concern in the Python world is integration tests and packages and support from your upstreams. Pip kind of sort of works in PyScript. You can deploy it. You can deploy lots of pure Python packages if you kind of fiddle around with them. But none of the popular libraries you want to use have their GitHub Actions config set up to run their library code inside of a browser in PyScript to make sure it keeps working because they care about front end. And the same is true of iOS or Android or a bunch of other target platforms which Python can target, but we just don't seem to. So beyond just getting PyScript into your GitHub Actions pipeline and making it easy for new users to build something in production quality with it, have you used PyScript to build a web front end? Why not? If your team ships a desktop integration, is it built with Python? Why not? For you personally, why can't Python fit down that tract housing driveway to get to that plumbing project? What about Python is too big for you? We need the proof points, the killer apps, the things that people point to and say, yeah, I want to build my front ends in Python, my back ends in Python, my mobile apps in Python. And we need those apps to be built for real. They need to be tested and deployed and live, not just demos, not just for conference talks. For my part, I'm trying, but it turns out that simultaneously designing and implementing multiple desktop apps on multiple operating systems and a bunch of the build tools you need to make them and a bunch of open source infrastructure that they depend on and use entirely on your own with crippling ADHD while the world collapses around you is kind of difficult. So no shade to anybody else who hasn't managed it yet, but okay. There's technology to put Python into new, smaller places, like web front ends, desktop apps, mobile apps, and we're not using it, but why should we care? It's neat that it exists, but why bother? Python's doing fine on the back end and in data science. Lots of other tools are doing fine on the front end. Why should we care if those tools have some success? The reason we should care is because we say we want people to learn Python. But we don't just say it, we ask them to learn Python. We tell them about Python. We extol its virtues. We don't just ask random people to learn Python either. Our community has made a point of reaching out to marginalized and underrepresented communities. PyLadies, Google Summer of Code, Black Python devs, many great grant projects under the Python Software Foundation's umbrella are all great. But by welcoming these people in, we're not just being welcoming. When we welcome marginalized communities, we are also implicitly asking for them to trust us, to be vulnerable to us. We say, write your applications in Python, learn Python, spend your time on Python, it'll be great. Look at all these cool demos we have. And we should be welcoming, now more than ever, because diversity, equity, and inclusion are actually good things. We should be proud of them. We should keep furthering those goals, even, or especially when we are being told not to. Presumably because we believe our tools will serve their needs, and broadly, I think this is true. So we should keep giving money to those efforts, and while I finish talking about this, let me just put some URLs and QR codes on the screen in case the mood takes you to maybe give them some money. But for those of us who already know Python, this seems like a small thing. If we want to tell marginalized folks to put their trust in the infrastructure and the community we have built, and then we tell them, check out this cool demo, you can totally do web front ends too, or check out this library, you could totally build a mobile app with this, but the reality of building those apps is that it's super confusing because nobody's actually building anything bigger than a demo, and nobody's actually shipping and testing the libraries and the tools that they would need, and they waste a bunch of time because what they wanted in the first place was to build a mobile app. Are we actually doing them any favors? This is absolutely not on the authors of any of those packages, or indeed on any of you. We're just doing our best. But it is still important that, as a community, we get together and insist on delivering on the promise that we have made, even on the promise that we have implied. Maybe for you, that has nothing to do with getting Python to run on a web browser or on a mobile device. Maybe you already maintain some critical infrastructure. I personally know that many of the people I can see do. But for those of you that have an application that could be finding that tract housing customer, this is a good opportunity, a call to action to do that. Now, in the grand scheme of things, it's a very small complaint about our ecosystem. Python is still huge and growing, and we are not in imminent danger of it becoming irrelevant. But we did ask people to learn Python. They learned it, and we did deliver on a huge amount of that promise. When we tell people you could build a web app with Django, that certainly works. There's none of that ambiguity that comes along with some of these more obscure targets. But there's no technical reason that Python should cut you off from front-end development or embedded development or desktop apps or whatever, because when we recruit a diverse audience with diverse needs, their needs will be different from ours. That is something that is inherent to diversity. So while we are trying to make sure that Python works, we should try to make sure that it works for all of us. I've been Glyph. Thank you very much for your attention. Please enjoy your mechanical excavation and mechanical excavation accessories.
Thanks, Glyph. I really dug your talk.